Okay, so from our original graph, we just identified the points. We flipped the points for our inverse and then plotted those. And yesterday we talked about, briefly, how the graphs of two functions that are inverses of each other will look as though they are reflections over a diagonal line. And we're going to talk more specifically about that right now. The diagonal line, well, I'll ask you, is there anybody who thinks they could go up there and draw in the line of reflection? The line of symmetry, I would say, between those two graphs, between h of x and h inverse of x. Anybody? How about if I offered you bonus points on the quiz? Oh, Andrew, all of a sudden you popped up. Wait a minute. Whoa, whoa, whoa. Raise your hand if you think you could do it. I saw. All right, I'm going to have Isaiah do it. But Andrew, you were quick to get that hand up. I just wanted to get a feel for. Grab one of those markers and see if you can draw. Excellent. You got it. Now, for the record, I said, if I offered you bonus points, who would do it? I never said that I would, did I? But I appreciate. I should actually take points away from you five for not raising your hand the first time. Don't be shy. But he's got it. I'm just kidding. I'll give you something. What is the equation of that line? Anybody know the equation of that line? It's like the perfect diagonal line. Micah? Y equals x. That's the, right here. That line has 1, 1, 2, 2, 3, 3, 4, 4. That's the perfect diagonal line. Draw that in on your paper and label that y equals x. We're just working on 6 from the homework answer. That's always the line. That if two graphs are inverses of each other, two functions are inverses of each other, then visually they will be a reflection of each other over that line. Does that make sense? Any questions on that? Okay, and then just to finish up with 6, if we wanted to kind of look at the domain and range. Let's go back to the original function. The domain of this, the lowest x value is -5, and the highest x value is 4. So the domain of this is from -5 to 4. And the range, if you look at your lowest y value, -4, and the highest, -1. Now, we're not moving ahead today onto a new topic just because there are so many little things in here I want to talk about. Set builder notation we just talked about. We're talking about the reflection over the line y equals x. I also want to talk about this. Write the domain and range using interval notation. I just used kind of inequality notation. Raise your hand if you've heard of or know what interval notation is. 1, 2. Kirsten, I know you do. Yeah, because that's what you did. That's why I asked you on your homework quiz. I was like, it's interesting that you wrote it in that format because I don't know how much you've done with it. But interval notation is definitely an Algebra 2 hotspot. Like a lot of things are going to be written in interval notation. We'll do more on that next week. But for now, let's talk about it. It's like kind of when you use brackets and parentheses. to show like when an interval starts versus when an interval ends. So this particular domain written in interval notation would look like this: -5, comma 4, and both would be with brackets. The brackets mean you include those endpoints. Okay, write that in on your homework worksheet. Again, you're keeping the worksheets, you're not handing them in, so this will be right in your notes. That's interval notation from that, when you do the smallest number to the biggest number, and then you decide brackets or parentheses on each endpoint depending on whether or not it's included. Because we have the or equal to sign, we use the brackets. Okay? On a side note, if I ever had this, -5, write this at the top, is less than x is less than or equal to 4, that interval notation would still be -5 to 4, but I would use a parenthesis around the -5 and a bracket still around the 4, because it is not inclusive of -5, but it is inclusive of the 4. Right? That's the difference between less than versus less than or equal to. Are we good there? Okay? If I did -5 to 4 this way, that would be inclusive of -5, and it would not be inclusive of 4. And lastly, and this can be tricky, and I'll explain more in a second, -5 and 4 both with parentheses. Okay? Now, this is interval notation for that inequality. What might people confuse that with? Right, a point on a graph. That's also the same way you would write the point on a graph, -5, 4. But they are totally different, right? It's like this word, thinking for those of you who like English. In one context, that says wind, right? Okay, something was blowing in the wind. In another context, that says wind, right? A windy road. Do they have anything to do with each other at all? No. But you understand what this means dependent upon the context in which we're talking. And it's no different in math. In this context of interval notation, that means that your x-coordinates range from -5 to 4. Look at your original function. -5 is the lowest x-coordinate, all the way up to +4 is your highest x-coordinate. And that would mean that we do not include the endpoints. Okay? But obviously, if we're talking about a point on a graph, that would be something totally different, right? -5, 4 would be, let's see, 1, 2, 3, 4, 5, 1, 2, 3, would be up here. It's got nothing to do with the domain. All right, so make sure we know that. As far as the range here, it goes from -4 to -1, so in interval notation, that would look like that. Okay, so we've got set builder notation, which is like inequality stuff, versus interval notation that we have to know. Okay, we have to learn to be able to read that and understand what that means. Now, back to the domain range piece. That was my original function. Now, after doing the warm-up and so on, if we're going to the inverse, we're flip-flopping these. So the range is going to become the domain. So that'll be -4 is less than or equal to x is less than or equal to -1. And the domain becomes the range. -5 less than or equal to y less than or equal to 4. Okie doke. Any questions there? Anything else on the homework? Yeah. Number 3. Oh, 3, definitely. Were you going to ask the same one? I thought about doing 3 as a homework quiz, but then I thought, you know what? I don't think we elaborated enough on this yesterday. So, well, I'm going to use a little bit what I just talked about. Okay? We're given g of x, and we're shown a picture of g of x, yet we're asked about the inverse of g. So if you were asked for g of 2, that would have been much more straightforward, right? Much to your liking. If we were asked for g of 2, we're being given our x coordinate and then just asked for the y coordinate. Okay? But we're asked for g inverse of 2. Okay? So this is the input, this is the x coordinate, I would say, of our inverse function, which means it's what coordinate of our original function? If it's the x coordinate of the inverse function, it's the what coordinate of the original, Maggie? The y coordinate. So they're really giving us the y coordinate of our original function. So if we're looking for a y coordinate of 2, that's going to be up here. Here's our point that has a y coordinate of 2. And what is the appropriate x coordinate that goes along with that? -1, 2, right? -1 is the x coordinate, 2 is the y coordinate. So that answer would be -1. Okay? That's one way of approaching it. If we actually wanted to, much like we just did on that back side, we could draw our own inverse graph. I could take this point, which is -1, 2, 3, 4, 5, -5, 0, and I could do 0, -5, so I flipped it. I could take another critical point, -4, 1, and make it 1, -4. Here's my next critical point, -1, 2, and I could do 2, -1. And I'll grab this one, which is 4, 3, and I can do 1, 2, 3, 1, 2, 3, 4. And I can connect all of these. First of all, do we see the reflection over that line? Okay? But now that I have h, or g inverse rather, now I can look at what is the y coordinate of, it would be 2 comma what? And if I go over 2 comma -1 would be the output. Does that make sense? So kind of showed you that in both respects there. Anything else on the homework? I kind of anticipate a lot of questions because it's a heavy topic. There's a lot that goes into it. So pass that forward. And I want you to start by getting out your notes from yesterday, because we did not finish the last 2 examples. So exercise 3 and exercise 4 on the back. Was anybody absent yesterday that didn't get back their quiz for corrections? You got everybody? Okay. Thank you. Okay, so exercise 3 here. Nope, you know what, I threw that out. Yes. Lydia, you need one? Yeah. Okay, I have an extra. You can come up and grab it. Yeah. Okay, so this is kind of getting at that question we just went over. Here's a linear function. We're given f of x. They want us to use the graph to answer this question. What is f inverse of 2? So we have a choice. We can either graph our own f inverse and see what point is on it, 2 comma what, or we can recognize that this 2 is the y coordinate. So right, if it's the x coordinate of the inverse function, it's the y coordinate of the original function. Do we follow that? So find a point on here that has a y coordinate of 2. And be prepared to share that. Find the coordinate on here that has a y coordinate of 2. McKenna. Does it 6, 2, 1, 2, 3, 4, 5, 6, 2. Correct. So this equals 6. Right? Again, I'll phrase it now that we have it. The original function has the point 6.2. So the inverse function has the point 2.6. Good? And then find f inverse of negative 4. Connor? Negative 3. So if he thinks that this is negative 3, then the original function should have the point negative 3, negative 4. 1, 2, 3, 1, 2, 3, 4. Correct. Good. Does that make sense to everybody now? A little bit more fluent with that? Determine the y-intercept. Now here's the y-intercept of the inverse function. That would be the same as what of the original? If you're swapping the x's and the y's. What do you think? The y-intercept of the inverse function is the same as blank of the original. Andrew? The x-intercept, right? Or flip-flop. So write that underneath there. It's the same thing. If they want the y-intercept of the inverse function, you can give them the x-intercept of f of x. So what is the x-intercept of f of x? Jake. What is the x-intercept of f of x? It's a number. Intercept means cross. So where is this function f of x crossing the x-intercept? 3. 1, 2, 3. So this is 3. Again with the swapping. The y-intercept of the original is the x-intercept of the inverse and vice versa. Now on the same set of axes, we're going to draw the graph. So when I go through and I say find critical points, I'm talking about points that you can actually identify exactly what the coordinates are. So on f of x, we have negative 1, 2, 3, negative 1, 2, 3, 4. So negative 3, negative 4 is going to become what coordinate, Aiden? Very good. I'm going to draw that. Our next critical point, 0, negative 2, is going to become what, Bo? Negative 2, 0. Good. Our next critical point is 3, 0. That's going to become what, John? Good. And our last one, 6, 2, we already said is 2, 6. And then we're going to connect these. And do we see the symmetry across the line y equals x? Hopefully, yes. Okay. Also, again, I'm going to point out, here is 0, negative 2. That's the y-intercept of the original. Yes? I know it's the y-intercept A because I'm looking at it, and I see that it's crossing the y-axis at negative 2. But B, I know that it's the y-intercept because it's got an x-coordinate of 0. Those two key features of intercepts. Okay? So when I flip that, that y-intercept of the original became the x-intercept of the inverse. Right? And the x-intercept of the original, which was 3, became the y-intercept of the inverse. Any questions there? What time do we get out of here? Oh, good. Perfect. All right, so that's exercise 3. Are there any questions on that? Everything's a big old swap with inverses. All right, we have a table of values for a quadratic. Yes? Okay, they give us a table of values. They've already graphed it. Graph the inverse by switching the ordered pairs. So that's pretty straightforward. Negative 2, 4 becomes 4, negative 2. Go ahead and fill in this table of values on your own, and then you can look up to check at the end. But I think we should all be able to flip the points without copying me. Go ahead then and plot all those points on your own. And connect them. And I'm going to label that. And raise your hand if you think you know what they're getting at in part B. What do you notice about the graph of this function's inverse? What do you think they're getting at? We talked about it yesterday. Three people. Well, Cameron, you have to know. Andrew might know. Everyone's kind of guessing. You're trying to kind of read into what are they getting at here? What were you going to say, Cameron? You could argue that it's a rotation, but we know that all inverses are not rotations, but reflections of each other. Yes. I don't think, well, again, I'm a teacher, so I kind of know what they're getting at. Maggie? Correct. This particular original function, when you take its inverse, is now no longer a function because it fails the vertical line test. We could have known that from the beginning. This original is a function, but it's not a one-to-one function, meaning its inverse won't be a function because this one fails the horizontal line test, right? So that should make sense. Think about your flip-flopping x's and y's again. If something fails the horizontal line test originally, then when you do that inverse, it's now going to fail the vertical, right? If it originally fails the horizontal, now it will fail the vertical. So what do you notice about the graph of the inverse? I notice that it is not a function. How could we have gathered that from either table, that the inverse was not a function? What about this table tells us that it's not a function? Go ahead, yeah, Evan. Two of the same input, 4 and 1. Yes? Which, if you look back, was because this had two of the same output, which is fine. This is still a function. But now your outputs become your inputs, and now it's not fine anymore. Okay? All right. We can now put that away. Kind of finish those notes from yesterday. And I, last minute, borrowed this from Mr. Hill to give you a second day of practice on inverses. So we're going to start by going through some of these kind of fill in the blanks. If a function y equals f of x has an inverse that is also a function, how do we represent the inverse? What's that notation look like? Oh, Madeline. What's the symbols for showing inverse? Y equals what? The symbolic way of showing the inverse of f of x. No. I'll give you a hint. It's in number 2. Read that sentence from number 2 and what part of that. Yes, the kind of looks like an exponent to the negative first. F inverse of x. I know you guys aren't really used to these fill in the blanks, but pronounced F inverse of x. Number 2 is kind of getting at that football analogy that I gave you yesterday, where these two machines literally undo one another, right? I'll just use the word undo. So if the one function multiplies it by 2, the other function is going to divide it by 2, right? They literally undo each other. Whatever f of x does to an input value, f inverse of x follows up by doing the opposite. Three we just talked about. The domain of f of x becomes the blank of blank. What do you think, Grace? The range of f inverse of x. Excellent. And the range of f of x becomes the blank of blank. Kirsten? Of? Very good. Okay. 4 we talked about yesterday. If f of a equals b, aka ab is a point that lies on the graph of, I'm just going to give you that one, f of x, then f inverse of b equals what? A. Good. AKA b comma a is a point that lies on the graph of f inverse of x. So I like number 5 because it makes it very simple. To summarize the concept of inverse functions as succinctly as possible, we switch x and y. When graphed correctly, f of x and f inverse of x should appear to be blank or mirror images of each other. What do you think, Bo? Reflections? Across the line, what's the equation of the line, Zach? The equation of the line that we reflect across. Y equals, very good. I want to jump down to 9. A little more practice with writing your own inverse. The steps that were outlined on yesterday's notes. Part A. Step 1, switch the x's and the y's. And then solve for y. Right? So we're going to subtract 8 from both sides. And divide by 2. So we'll get y equals x minus 8 all over 2. And then I want to jump to D. Same type of problem. It just starts with f of x. So if you want, you can first rewrite that under the y equals format. And then switch the x's and the y's. And solve for y, which is going to be first adding 4 to both sides. How do I get rid of that negative 2/3? How do you get rid of that? Kaylee? Far Kaylee. Divide by negative 2/3, but when you divide by a fraction, it's the same as multiplying by the reciprocal. Usually you don't divide by a fraction, you instead multiply by the reciprocal. So I'm going to multiply both sides by negative 3 over 2. And when I do that on the left-hand side, I have to distribute. Negative 3 halves times x is negative 3 halves x. What is negative 3 halves times 4? How many halves? Negative 3 halves times 4 is how many halves? What's negative 3 times 4? Negative 12 halves. And negative 12 halves, that's silly. What's that whole number? Negative 12 halves is 6. And there's your inverse. Okay? I want you to finish this worksheet as your homework. Okay? So anything we didn't get to front and back, that's your homework. Understand? You can do it right on this worksheet. Okay? Do it right on this worksheet because there's some graphing there on the back. No, I can look at them if you want me to check them over, but then I'm going to give them back to you.